Hello Western. So picking up from where we left off in the previous video, I want to now start talking about the factors that affect the speed of a wave. So again, focusing on sinusoidal waves, if we think about a single point inside the medium, as this wave moves to the right, and as this disturbance moves to the right, this point is going to get displaced so that it moves up. Eventually it'll start to move down to the bottom, and then eventually it'll return back to its equilibrium. And that full oscillation in that particle takes one period of time. Now, the reason the particle undergoes one full oscillation, if we think about this, is because this disturbance, which I have highlighted here in green, moves through that point. And this amount that I have highlighted in green is equal to one wavelength. Okay? So the disturbance, as we can see in the second picture here, has actually moved forward by one wavelength during this time that is equal to the period. So the disturbance travels at a speed that's equal to the wavelength divided by the period. Or, writing that in terms of frequency, it's frequency times wavelength. Now this is generally, I think, a very easy formula to remember because even if you forget, if it's wavelength divided by period or wavelength times period, you can always just use dimensional analysis. It has to have units of meters per second because it's a speed. Now, let's go ahead and work through just a very simple example. So in the figure below, I have a drawing of a wave, and I say that this wave has a frequency of 10 Hertz. So the question is what is the speed of this wave? So in the previous slide, I said that the speed of a wave is equal to frequency times wavelength. Looking at this figure, we can see that one wavelength, let me highlight that, so one wavelength is something like this. We can see that one wavelength is equal to 10 meters. So plugging this in, 10 Hertz for the frequency, 10 meters for the wavelength, this has a speed of 100 meters per second. And that's what I show here on the next slide. So in the next example, we want to consider light. Light moves at a speed of 3 times 10 to the 8th meters per second. The human eye is most sensitive to a wavelength of 545 nanometers. What is the frequency of this light? So again, all we have to do is use the same formula again and just rearrange it to solve for frequency. So speed is equal to frequency times wavelength. So the frequency is equal to the speed of the wave divided by wavelength. Plugging in the speed that we have and the wavelength, we see that the speed of the wave, the frequency of the wave is 5.5 times 10 to the 14 Hertz. Okay? So that's how we can relate the speed of the wave to the frequency and the wavelength, but what actually determines how quickly a wave propagates through a medium? So I'm going to give you just a bit of an example of this. So consider a whole bunch of masses that are connected together by little springs, like I have shown here in the figure. So if I apply a force upwards on this mass is going to move upwards in response to that force. And when that happens, it's going to stretch the spring out in this direction. Now that spring being stretched out is going to cause a force on the second mass that's pointing upwards, and it'll cause a force on the first mass that's pointing downwards. So as a result, the first mass moves down, and the second mass moves up. Now at this point I'm going to apply a force to the first mass to keep it fixed in place. But if we think about this, the second mass is moved up, so this spring's stretched out, and this spring's stretched out. So there's a spring force pushing up on this mass, and there's a spring force pushing up on this mass. Now, as I said, I'm going to hold this mass on the left in place, but the mass on the right is going to move up. So at some time later, the disturbance propagates forward. And it's just going to continue propagating forward because of these forces that are caused by the springs being stretched. So if we think about what determines how quickly this wave propagates, well, it's basically determined by how quickly these masses are being pulled back towards equilibrium. So for a string, for example, the speed of the wave is equal to the square root of tension divided by mass per unit length. Okay? So hopefully this makes sense. The larger the tension is, the faster the wave, or the string gets pulled back towards equilibrium. And the larger its mass is, the harder it is for the string to get pulled back to equilibrium. It's got more inertia, okay? Now, remember I said for an ideal gas, or actually any gas, the equilibrium condition is that the gas should have a uniform distribution, a uniform density, okay? So it turns out that the speed of a wave in a gas is just related to its RMS speed. In fact, it's just proportional to that. This is constant here, this gamma, which is called the adiabatic constant for a gas. Okay? And this should make sense because the amount of time it takes for the air to rush into an area where there's a lower density should just be related to the speed that the speed that the air moves. So we can see, of course, then the speed of a wave in an ideal gas is proportional to temperature and inversely proportional to mass, just like the RMS speed was. Now, in general, the speed of a wave is going to be equal to the square root of some sort of restoring factor that describes the strength of the restoring force that pushes the medium back to equilibrium, divided by an inertial factor, which describes how hard it is to move these points at all. And so, I think that's where I'd like to end this video for now, and in the next video we're going to start talking about how we can mathematically represent sinusoidal waves. And this is a very important thing because later on in this class we're going to start talking about certain types of wave phenomenon like standing waves and beat notes and things like this, and the only way we can explain these is if we have an equation we can write down for the waves.